Hi there, in this video I'm going to explain the Newton Raphson method. Okay, so this is another way in order to find an approximate solution for the root of an equation. Okay, so in the previous two videos we've seen the iterative method, which is one way in order to find an approximate value for the root, but another method is called Newton Raphson. So let me explain the Newton Raphson method. Okay. And I've got a selection of screenshots in order to explain the concept behind the Newton Raphson method. So let's view these screenshots. Now, looking at the first screenshot, supposing if I have the graph of y equals f of x. Okay, so if I have a function y equals f of x, and if I graph that function, remember, the root is the point of intersection of this function with the x-axis. So the root I called alpha, and I've circulated that root in red. Okay. Now, the idea of Newton Raphson, so let me explain the idea. So let's go to the next screenshot. Now, supposing if we have a first approximation for this root, so I call this first approximation x is equal to a, okay? And if I drew a tangent at x is equal to a, so this blue line, so I hope you can see this blue line, so the blue line represents the tangent to the curve y equals f of x at x is equal to a, okay? And if you draw this tangent, the point in which this tangent crosses the x-axis will give a value which is closer to the root for this equation. Okay, so the point where the tangent crosses our x-axis, I highlighted that in green. Okay, and as you can see, that point highlighted in green is closer to the root for this equation, which is highlighted in red. Okay, and if you continue Newton Raphson, so if we use this new value of x, and if we substitute it back into the Newton Raphson formula, Newton Raphson is an iterative formula, so if you substitute it back into the Newton Raphson iterative formula to calculate the next x value, that next x value will be again the point of intersection of that tangent with the x-axis, and that point of intersection of that tangent with the x-axis, it will give you a value which is even closer to the root for the equation. So if you continue this process, these tangents that you draw will become closer and closer, so the cutting points of these tangents will become closer and closer to the value of the root itself for the function given. So let's go back to the paper and pen. Let me explain the Newton Raphson iterative formula. Okay, so remember, we have this function y is equal to f of x, okay, and supposing if we have our first approximation, so if I call this first approximation for the x value xn, say, so xn is our first approximation for the value of x. Okay, now remember, when we looked at that screenshot, okay, so one of the screenshots, the idea was to draw a tangent at that x value. So we draw a tangent at the x value xn. Okay, so remember, from our theory of tangents, in order to work out the equation of this tangent, we need the gradient of the tangent. So the gradient of the tangent, so gradient of the tangent, so let me denote that by m meaning the gradient of the tangent. So we differentiate the equation of the curve, so it will be an f primed x, and after you differentiate, to find the gradient you replace the x by xn. So the gradient of this tangent will be f prime xn. Okay, and in order to find the equation of this tangent, so we can use this result. So the equation of the tangent at our point xn. Okay, so xn is our first approximation, and the corresponding y value, if we put xn into the curve equation, we'll get the y value, and that will be f of xn. Okay, and in order to work out the equation of the tangent, I use this formula, y minus y1, and that is equal to m is the gradient, into x minus x1. Okay, so in this formula, x1 and y1 are the coordinates of the point, okay, and the coordinates of the point that the line passes through, or the tangent passes through, are xn and f of xn, and m is the gradient of the line, so the gradient of the tangent is f primed xn. Okay, so in this formula, you may have seen this formula, y minus y1 is equal to m into x minus x1. x1 and y1 are the coordinates of the point that the line passes through, and m is the gradient of the line. Okay, so if I replace what we have into this formula, we're going to have y minus y1 is f of xn, that is equal to m, which is f primed of xn, into x minus x1, which is xn. Okay, so if I rearrange this, we're going to have y is equal to f of xn plus f primed xn into x minus xn. Okay, so all I've done simply is taken the f of xn to the right. So by taking the minus f of xn to the right, we get plus a plus f of xn. Okay, now remember, in the screenshot, the idea of the Newton Raphson process is the point where the tangent crosses the x-axis, that point will be closer to the root for the equation. So let's find the point where the tangent crosses the x-axis. So remember, when our tangent crosses the x-axis, y is equal to 0. So when tangent crosses x-axis, y is equal to 0. So if I replace the y by 0, we're going to have 0, that is equal to f of xn plus f primed of xn into x minus xn. Okay, and let's find the value of x, so the x coordinate where this tangent crosses our x-axis. So if we rearrange for x, okay, so in this case, let's do some rearrangement. So first of all, if I multiply the brackets, 0 will be f of xn plus x f primed xn minus xn f primed xn. Okay, and if I keep the x f primed xn to one side, so if I keep the x f primed xn on the right hand side, and if I take the remaining terms to the opposite side, so I'm going to have, okay, xn f primed xn minus f of xn, okay, and x therefore will be, so if I divide both sides by f primed xn, I'm going to have xn, so xn f primed xn divided by an f primed xn will give you xn, minus, so minus f of xn divided by the f primed of xn. Okay, so if we call that x value, supposing if that tangent crosses the x-axis at a point xn plus 1, okay, then the equation ends up to be xn plus 1 is equal to xn minus f of xn divided by f primed xn. Okay, so that is the point where the tangent crosses the x-axis, and that point is, remember the idea with the screenshots, the idea behind Newton Raphson, the point where the tangent crosses the x-axis will give you a value which is closer to the root for the equation. Okay? Now, there is an exception to Newton Raphson, so let me explain the exception again by means of screenshots. So here's the first screenshot. Now, in the first screenshot, I have a curve y is equal to f of x, and I have the root for this equation. So the root again is the point of intersection with the x-axis, and I've highlighted this root that I've called alpha in red. Now, remember the idea of Newton Raphson, supposing we have a first approximation for the root. So I call this first approximation x is equal to a. And in the next screenshot, if I draw a tangent at that point x equals a, so the blue line represents the tangent to the curve y equals f of x at x equals a. Okay, now I want you to note that the crossing point of that tangent with the x-axis gives us a value which is further from the root. Okay, so the crossing point of that tangent with the x-axis are highlighted in green, and as you can note, so as you can observe, that crossing point highlighted in green is further from the root of the equation, which is highlighted in red. Okay, so there are some exceptions to Newton Raphson. So that ends this video, so I hope you found this video helpful. In the next video I'll go through some examples explaining how the Newton Raphson method is applied, so I hope to see you then.